In particular, I would like to highlight Gilles Muller, who's the first one listed for Coccinelle, who had the initial idea for this project at another international conference far from home, just like the one where we're attending today, or some of us are close to home. But, so the application area of our work is the Linux kernel. When we started the project in 2004, the Linux kernel was 4 million lines of code. We thought that was a really huge software project. Today it's around almost 27,000 million lines of code, and it's still rapidly growing. It has frequent changes. There are certainly many new features, but there's also changes to improve performance, correctness, fix bugs, improve security, and so on. So the question that we asked in 2004 was, how can we easily perform evolutions in such a large code base? So here's an example that was relevant at that time. So in the Linux kernel, they have the functions kmalloc for allocating memory and memset, which is the familiar user-level memset, which you can use afterwards to zero memory. And so someone thought it was a good idea to merge these two functions so that we could have a function that allocates memory that's going to be initialized to 0. So that function is called kzalloc. So here's an example of the change to introduce the use of kzalloc. First we have our, sorry, we've lost all our hardware here. First we have our call to kmalloc. Sorry. Here we go. Okay, so we have our call to kmalloc, and after that, somewhere afterwards, we have a call to memset. And the change that we want to make is just to turn, basically it's very simple, we just want to turn the letter M into the letter Z. That's just changing one character, and then we want to remove the call to memset, which is not needed anymore because kzalloc is going to do the zeroing directly. So you can see this is not a very complicated change. On the other hand, it's not so easy to find the 1,500 places that this change can apply, because there are far more than 1,500 calls to kmalloc in the Linux kernel. You wouldn't want to have to go and look through all of them. There are lots of calls to memset in the Linux kernel. They don't all have 0 as a second argument. Even the ones who do, they might be reinitializing the data, or they might be initializing it the first time. It's only in the second case that we can use kzalloc. So it's a bit complex to find opportunities for this change. So basically, in general, we have these kind of pervasive changes that we want to make. Some of them are a bit complex. In general, the kernel developer, the person who's the expert in the software, knows what kinds of code they want to change, and they know what kind of changes they want to make in that code. And everything is very systematic and deterministic and so on, but what they need is some way that they can communicate their requirements to some kind of tool to perform the change automatically. So at the time, there were some tools that would help with some kind of systematic changes to software, but those tools required interacting with the code at the abstract syntax tree level. And some very kind of complicated abstract syntax tree traversals, in particular for just simple integers, because they're expressions, they're constants, they're numbers, they have a certain type, and so on. So we want to get away from all of these compiler-specific issues or compiler-like issues and return to the source code level, which is what the Linux kernel developer is most familiar with. So the idea of my colleague Johan Padiolo, who I don't know if anyone is familiar with the tool semgrep, but he made the tool semgrep many years later. His intuition was that the key to reasoning about changes for Linux kernel developers is to talk about patches. They make patches, they send them to other developers read them, and so on. And so here is a typical patch for the change. I mean, it's the change that we just saw. You have some line numbers which indicate where the patch should apply. Actually, the file name is available somewhere else. I just cut off that part. We have the lines that we want to remove and the lines we want to add. And then in between, we have some other context code. It's not going to be changed, but it's going to help the patch tool be sure that it's applying everything in the right place and nothing strange has happened. So this is a very nice tool. It's very deterministic. The change is easy to read. We know exactly where it's going to happen. It's a way of communicating changes from one developer to another. Unfortunately, it's very specific to a particular site in the code. So the idea of our tool Coccinelle is to take these kinds of changes, just line by line, remove something, add something, and abstract over them so that the change can be applied across an entire code base. So we have two basic ideas. One of them is basically, if we look here, some of these terms are not very important. So kmalloc, for example, is very important. That's the key to what we're trying to do. And fh, for example, is not very important. That's some random variable where we want to store the result, but we don't care what it is with respect to the change. And similarly, these arguments are also not very important, the specific type of fh, for example. But then some other things are, some of the arguments are important. For example, the 0 on the mem set is important. So it's the developer who knows what's important and what's not. And what we do is we give the developer a way to abstract over the unimportant things by introducing what are called metavariables. So metavariables are variables in your transformation rule that are going to be bound to sub-expressions that you don't actually care very much about. And then we also have this code in the middle. We also don't really care about that. And so you can replace that by ... So ... kind of intuitively means whatever stuff is in there. In the context of Coccinelle, it actually describes a control flow path. So if we have the rule we're going to end up is going to look like this. And we have our kmalloc, and then we have ... and then we have memset. And that means once you start executing kmalloc, afterwards your execution is going to do whatever it does, might go around loops, go around ifs, and so on, but it's going to end up at the memset. So this is the basic idea. With this, actually, you have a working change specification. You can take these 5 lines of code, and you can apply it to the Linux kernel, and it will, at least in 2004, when there were lots of opportunities, it would go around and change 1,500 probably code sites. But this is not, if you think about it a little bit, this is not completely safe because we don't actually know what's going on in that ... region. So there's a little bit of extra syntax. So we really did not want to stray too much from the C syntax, but here we were forced to do that to give a little bit more expressiveness, a little bit more chance of correctness. So you can say some things that should not occur on that path. And so what we have here is a somewhat complex means of saying this is an assignment, any kind of assignment with x on the left-hand side. X is the metavariable that we're using for the result of kmalloc. If you have some assignment that involves x, then that's going to be risky. We don't want to do that. And this one here is if you have a function call, if you pass a uninitialized region of memory to a function, perhaps there's a high chance that you are going to initialize it. And in both of these cases, and then the memset would be to reinitialize the thing instead of initializing it for the first time. So we have these little protections. Coccinelle is a tool that allows you to specify what you want, and then it does what you want. It doesn't prove that your transformation is correct. You still have obligation to go through the code, the changes, and see see if it's what you actually wanted. But I think the knowledge of the Linux kernel code and the typical coding patterns gives you a good chance that everything will work out the way you expect. So in Linux 2.6.14, so this was a long, long time ago, there were 335 uses of kzalloc. So those are ones that a human had put in by themselves. This is about the time when the function was introduced. And then this semantic patch will add over 1,300 more of them. But then in looking through the code, one might realize that actually there's some other situations, or one might just think about things and realize that there might be some other situations. So we can generalize things a little bit here. What I have done is actually, kmalloc, it has 2 arguments. The first one is the size of the region that we want. And actually, there's multiple ways that you can express the size of something. So in particular, you can say size of the type of the thing, or you can say size of a dereference of the thing. So here we're allowing those 2 options. either size of, so this is called a disjunction. It lets us, it's a parenthesis, bar, parenthesis. It lets us say we would like to match either this or that. So we have the size of the type, or another way of referring to the size here. And then in the mem set, you can also have the two different size options. So Coccinelle not only gives you an easy way to make your rule, it also lets you refine your rule in a very easy way to consider more cases or to protect against more issues. And you can see also here that in the original patches, they were talking about real lines of code. In these, what we call semantic patches, you can just make whatever you want as a line. So it's not really tied to the white space and so on. On the other hand, it does actually preserve all the white space and comments that were in the original code in whatever it thinks is an appropriate way. And so this adds 114 more uses. And then we submitted a patch based on this to the Linux kernel developers, and this was like the first large-scale thing that we did for the Linux kernel. So I'll just give a couple more recent examples that are a bit more complex. I'm not going to go into them in great detail. This is one where something that a Linux kernel developer asked for recently. You can read it. Since slob was removed and since commit whatever, it's not necessary to use call RCU when the callback only performs kmem cache free. Use kfree RCU directly. So the point here is that these are functions that are very specific to the Linux kernel. We're using the knowledge of the developer, which is that certain things are not necessary anymore, and we just want to express that and clean things up according to some change that has recently happened in the Linux kernel. So here is an example of the typical change. We can look at that again here. We can see here in a bit more detail what kinds of changes are going to be needed. So we have this call RCU here. That's actually the thing that we're most interested in. Call RCU has a second argument, which is the name of a function. And when we look at that definition of that function, actually the function is very simple. The only thing it does is call kmem cache free. So these are the kinds of functions. This is a situation in which we can make the change. This function can be expressed in a variety of different ways. It can just call kmem cache free only, or it can have some intermediate variables like we see here. We also want we check that that function has the right form, but we also want to be sure that the function is not used for anything else. If we're going to remove the function, if it's used for something else, that would not be good. So we can add in some checks along the way to ensure that everything is in the way that we expect. Maybe the developer afterwards will have to deal with some of the cases by hand. And so we end up with this transformation rule. Basically, this has three parts. One of them, the first part on the left here, is matching the kinds of things that we're interested in. You see here basically this call to call RCU, which is the one that we want to change. And here is the definition of the function in various different forms according to whether there's some intermediate variables that are used. So that's like this part here is matching to see if everything is in the right situation. So the tricky thing here is we have actually two different blocks of code that we have to study and be sure that everything is coherent between them, because Coccinelle works on one function, one top-level object at a time, a function definition, data structure definition, whatever. So we have to look at these two separate things, ensure that they are both in the right form. What I have here in the middle is going to ensure that we don't have any other uses of the function name that we matched here. So basically, the good ones here are at particular positions, and so you can have a special kind of position variable that's going to record it's at that position. It's going to collect all the positions of the good ones, and then in this rule, it will check and see if there are other positions that would be some kind of other uses of the function. So if we have things that match the rule on the left and we don't have anything that matches the rule in the middle, then we can apply the rules on the right-hand side and make the transformation. And so all this happens with these dependencies you can see to ensure that everything is working in the right way. So this made 11 changes. It's not a huge number of changes, but on the other hand, it's across the entire kernel. There's lots of different things you have to check, and those things are all done automatically, systematically, and so on, and then the whole change got done at once, basically. So here's one more example. This is a very recent example. Recently in the Linux kernel, maybe with the advent of Rust, there's been interest in maybe more safe coding strategies. So they've started using a thing called scope guard, basically. This is something that lets the lifetime of basically a critical section. So you take a lock at the beginning of a scope, and the lock is going to be unlocked at the end of the scope automatically. So it's basically making the lifetime of some resource correspond to some scope in the C code. And so what we're trying to do here is take uses of just random. Here we have a mutex lock at the top, and a mutex unlock here at the bottom. So we find these uses of mutex lock and unlock and see if they actually correspond to a scope region, something we can consider to be a scope region. There's two different operators. There's scope guard, where you create a new scope. There is guard, where you just work until the end of the function. So there's things that you have to choose between. And then at the end, which you can see here, we have completely removed the out label. We have turned the goto into an immediate return. And so there's some cleanups that you have to do after making the transformation. So what we aim for is to be able to make the transformation in a way that corresponds to what the human developer would do, at least as close as possible. All the indentation, white space, and so on is going to be managed automatically. So this rule is 650 lines of code. It took the intern a few months to work on. On the other hand, the intern didn't have any previous experience with Coccinelle. He didn't have any compiler experience. He didn't have very much Linux kernel experience. So he got through all of these things. It updates, just the case of mutex lock, it can update over 4,000 different files. I think it's like 15,000 code sites. On the other hand, this is not something we would want to just dump all the results on a Linux kernel developer. Coccinelle is a tool to help you do things. It's not a replacement for actually studying what you've done and being sure, arguing that what you've done is correct, and so on. Okay, so it's been going on, been released for almost 20 years now. We want to see, how has it been used by Linux developers? Have we succeeded in making something that people have as part of their normal toolbox? So the numbers have gone up and down. It seems like it was more popular, more widely used in the middle of the 2015 and so on. So I'm not sure, I still see people actively using it. This is several hundred commits per year. And it's also possible that maybe they're not always actually acknowledging the tool every time that they use it. But in general, we have gone from something that was mostly used by us to something that is mostly used by Linux kernel developers. So I think it has been basically a success. So what we have made is a user-friendly tool for updating C code at large scale. It's been inspired by developers' needs and expertise. So I think that was really the most important and most original point, is that we thought about really what the developers want and tried to figure out for them what they wanted somehow and manage somehow to get at the right spot. It allows developers to rapidly react to changes in the code base. Over 12,000 Coccinelle-based commits are in Linux kernel, and we are now working on Coccinelle for Rust, which is also of interest to Linux kernel, and version for C++. There's a prototype for Java, and it is all publicly available. So then the question is, have we and have all the various tools that have emerged over time for finding patterns in code, finding bugs in code, and so on, have we solved all the problems? Have we solved a tiny part of the problems? Have we solved any real problems at all? So I think this is a question. So another part of my research is to study Linux kernel performance. Basically, what this involves is studying the behavior of some benchmarks, identifying bottlenecks, trying to figure out what's going on, maybe trying to propose solutions for the problems that we observe. So we often use something with the NAS benchmark suite. These are very simple applications. They're high-performance computing-like applications. Basically, I was looking at one which is called BT, and it does something. I don't know what it does. The interesting part is that it has n tasks that run on n CPUs. So this seems like it should be a simple thing to manage from an operating system point of view. Just put all those tasks on their different CPUs and let them run. So we try this on a 2-socket Intel machine with 64 CPUs. So I made some little graphs, what is the running time of this application. And what you can see here is, you can see little dots. You can see most of the time it is fairly stable. Fairly stable mostly here, but maybe about 20% of the time it gets 20% slower, which is a bit surprising. So here what we can do is we can look at the actual execution and see what's going on. So in these graphs, we have the horizontal axis, which is the time, and the vertical axis, which is the set of CPUs. And the colors represent the PIDs, so they represent different tasks, but the colors are being reused, so there might be 2 green lines and so on. So this is a fast run. What I said the ideal situation would be is just we put the tasks on the cores and they just sit there and run as fast as possible. That's not what seems to happen in practice. They seem to move around a little bit, but it doesn't seem very distressing. They seem to keep going, and we get reasonably good performance. On the other hand, here's a slower run. I don't know if you can see from the audience what the difference is, but I'll highlight that in a minute. And here's a really slow run. So what the difference is the slower run has some gaps in it. So there's some spaces where actually there is a core available, but nothing is happening on that core. And one of these gaps is fairly small, but the one at the bottom is fairly big. And then if we go to the very slow run, then we see actually there's a huge gap. This is like more than 3 seconds where our threads are just not being placed on the CPUs in a desirable manner. So, I mean, from the size of these things, we can see maybe there's some connection between these gaps and the performance. So what's the impact of these gaps? The impact of a gap depends on why the gap is there. If there's nothing to do, then you will get a gap. And if there's nothing to do, that will not have any impact on the performance either. The other situation where you have a gap is that actually my graphs, they're only showing where things are running and not where things are waiting to run. So a case where you have a gap can be where there are 2 tasks that are trying to run on the same CPU and another CPU that's doing nothing. And that's very undesirable because those 2 tasks are going to be competing with each other. Basically, they'll go twice as slow. And these applications also synchronize a lot, so they will actually slow down everyone else. So if I study a bit in more detail these traces, I can see where the gap is coming from. We are definitely in the second situation. We can see where the gap is coming from, which is a thing called NUMA balancing. So we have 2 different NUMA nodes. NUMA means like there's a certain amount of memory that's located over here and another amount of memory that's located over here. And the memory manager has had the idea that actually the tasks over here would really rather be referring to the memory that's over here. And so it has 2 ways of dealing with the situation. One of them is to swap tasks. So it finds a task here that wants to be here and a task here that wants to be here, and it just swaps them. So that's fine. That's not going to have any detrimental impact in terms of who's running where. The other option it has is actually it doesn't find anyone to compensate, and so it just takes a task that's over here and moves it over here. So basically now we have our machine has 32 CPUs on each NUMA node, so now we have 33 tasks over here and 31 on the other side. So from that we get a gap, and so that introduces overloads and that slows things down. But the question is, I mean, the introduction of this overload and this issue is just how the system works. It's got these heuristics, it does things, some of them are not so good. But the question then is, why doesn't the overload get corrected? How can it go along for 3 seconds, which is a huge amount of time from an operating system point of view? So we have this load balancing, which is another part of the scheduler, which is supposed to, we have our idle CPU, it's supposed to go around and try to find load tasks that it can steal to bring back to run on this CPU so that everybody will be doing something. So this is kind of a little flow chart that describes how I mean, load balancing is good because it brings stuff to idle places and better uses the CPU. It's bad because it has the tasks bouncing around the machine. So it's kind of a trade-off. Do you want to have your tasks bouncing around the machine? Do you want to move? And so on. So it's got a lot of constraints. There's a lot of things it checks before actually trying to do load balancing so it doesn't waste time doing something that's not desirable. So we have various functions. Should we balance? Find source group. Group is, the whole thing is hierarchical. We do load balancing at a certain level. At that level, there are children, which are groups. They're groups of CPUs that we might like to steal things from. So we try to find the busiest group, and then inside the busiest group, we try to find the busiest run queue. So that's what these two things here are. So we make all these checks. If we keep going, then we try to see, we have found our busiest run queue. We try to see if there's anything we can steal from it. If we can, that's good. If we cannot, then there's another kind of load balancing, which is called active balancing, which is somehow more aggressive. In particular, it will steal a task that's actually running at the moment. So we have all these different tests, and we make some decisions based on things. So the question is, where do we get off track in this process? Okay, so now I'm going into a lot of very low-level scheduling issues. On the one hand, I don't really expect you to care very much about them. On the other hand, my point is that they are very low-level and very hard to understand. So find source RQ. Remember, we have 32 CPUs available on each side. We have 33 tasks that are trying to run on one of them. One of those CPUs is overloaded. So find source RQ almost always decides that the load is already balanced. So maybe it sees this extra task, but it decides it's not a good idea to move it around. So there are some flags. One of them is called migrate util. One of them is called migrate task. They are associated with different strategies. Somehow it decides to pick migrate util. Somehow it decides to pick migrate task. Migrate util is very conservative. The way we want to get our load balancing to happen, we'll need migrate task. Another issue is if this active balancing, which is supposed to be our last hope. This has 2 constraints. One of them is this migrate task thing. So if we have changed, the first thing I did was to brutally change migrate util to migrate task, because migrate util did not seem like it was going in the right direction. So I've taken care of the first one, but then we have the second one. We have a counter. The number of load balances that failed, that should be greater than some other flag here. This turns out to be, it has to be greater than 4. 4 is just some random number. It's not clear why they chose, it's his nice tries +2. Why +2? Nobody knows. So 4, it doesn't seem like a very high barrier to high threshold to cross. We had more than 3 seconds of idleness. This load balancing may happen every 4 milliseconds or something like that. So we have plenty of opportunities. But if we look at actually that counter, then we can see that it very courageously, it starts out at 0, it courageously goes up, up, up. And then it comes to 3 or 4 or something like that, and then it just gets shot back down to 0 again. So that's what it does. It just keeps going up and down and up and down and up and down. So actually it turns out that reaching 4 is actually a very hard thing to do. So again, we have these 2 functions. The ones at the top If we decide that there's no overloaded run queue, then we fail. If there's no group that is overloaded, then we also fail. Remember, we have definitely overload, and so it's very surprising that this happens so frequently. So again, we can go back and look at the code, see what's going on. So there is some kind of thing which is called FBQ type. So it basically chooses a run queue in 2 steps. The first one is it analyzes the entire group and sees what is its FBQ type. And this FBQ type is some piece of information. It's going to determine what kind of tasks we will try to steal from, what kind of run queues we will try to steal from. So we have made some decision in advance. And the problem is that between the time when we make that decision and the time when we actually steal something, remember we have many cores on our CPUs on our machine, they're all running along by themselves, and the situation will change. And then the FBQ type that we had initially is not appropriate anymore. Our FBQ type is not satisfied in what we see, and so then we give up again. That's one issue. Another issue is a group. Remember, we have basically, if you think about the groups as the different NUMA nodes, remember we have 33 tasks trying to run on 32 CPUs. We should certainly find a busiest group, which is that one, which is overloaded. But things can go wrong there as well. For one thing, there can be migrations, other migrations that are happening at the same time, actually totally useless ones, where that extra thread is just bouncing back and forth between 2 CPUs on the machine. And if the CPU that is trying to steal it onto the other socket is counting the number of threads available at the same time that the thread is bouncing back and forth, one of them will be missing, and it will look like the overload is not high enough. And then another issue is that actually part of the whole load balancing process involves waking up a kernel thread on the socket that is trying to steal. And in that case, it looks like that socket is full up already. So again, we have some kind of strange concurrent effects that we make our decision in the wrong way. So once we have tracked down all of these issues, so I spent, I don't know, maybe 6 months, not continuously, tracking down these issues, trying to figure out what was the problem. I also presented some numbers at a Linux kernel conference, and no one jumped up and said, it's obvious that this is what your issue is. If you manage to track down all of these issues and figure out some hacky way to mitigate the problem, then here's the blue line. This is 500 runs now. This is the normal Linux kernel. The brown line is the one where I have fixed everything up. So we've got it's almost flat now. It's a little tiny increase at the end. I'm not sure what the issue is there. I just show also the case where we just pinned the threads onto the core so we can't move anything at all. And that one also has a little rise at the end. So it doesn't seem like it's a scheduling issue. So basically, as I said, I spent months of work to identify all these problems. There's a lot of subtle details. There's a lot of variables that have funny names, flags that have funny names. It's not really clear what any of this means, how these things are supposed to fit together, and so on. These things have different values, +2, +4, and stuff like that. What do the values mean? Why were they chosen? All of this information is perhaps in the head of some people, but it's not even clear that it's all there because the code is changing all the time. Somebody realizes they have a performance problem, they make some little hack and it goes away. If they're convincing enough, it gets into the Linux kernel, and so we have just this kind of random thing. So the big problem is, how can we understand what's going on? How can we keep the different parts of the code synchronized over time? And all these kinds of things like finding null pointer dereferences, finding buffer overflows, finding inefficient calls to kmalloc and kzlloc, those are all wonderful things, and certainly buffer overflows or whatever will cause many security problems and so on. But there's a whole other world of these kind of algorithmic decisions that are being made and whose meaning has not really been preserved and whose interaction with other algorithmic decisions is not really clear. So what we've done is in the last year or so is to maybe go in completely the opposite direction. So with Coccinelle, we tried for something maybe very approximate, something that exploits the developer's knowledge in a very developer-friendly way, no guarantees of correctness, just it does what you tell it to do, and then you try to cope with the result. Now we are thinking about formal verification. What we want is to specify what's going on in this code, and hopefully if we can, when we make these specifications, maybe we can learn something about what's going on, and maybe we can learn something about how things relate to kind of preserve the knowledge about how things relate to each other, different parts of the code that seem unrelated but actually have some impact. So the basic idea is to write the specification describing what the code is supposed to do, and then use some kind of tool that will help us ensure that the specification does what the code actually describes what the code is actually doing. So we have some kind of documentation. Of course, the Linux kernel has lots of comments, but this is natural language. It's open to interpretation of the person who wrote it, the person who reads it. So specifications should somehow be a little bit less ambiguous, at least. On the positive way, thinking very hard about what this code does, all the code paths, all the ways it can be called, and so on. It can highlight inconsistencies, bugs, and missed optimization opportunities. So we've only been working on this a short time, and we have found all of these things basically in every example we've looked at. Specifications are unambiguous and describe what the code does. On the negative side, I'm sure you have anticipated this, writing specifications is just really hard. Reading specifications is also pretty hard. I think there's a great need for some kind of language that makes the whole thing more user-friendly. And then can we hope to maintain them? The developers already have to understand the code, and they have to maintain the code. Can we expect them to maintain the specifications as well? Can we expect the people who pay for Linux, which is basically Google, Facebook, Amazon, and so on, Huawei, and so on, can we expect them to start hiring verification engineers to accompany their developers as every little change to update the specifications at the same time? And of course, there's no magic bullet. Specifications are whatever they are. If the specification is wrong, if the specification is not what you intend, the code will, and you check it to match the code will not be doing what you intend either. So there's the fact that verification is very hard, but some people in recent years have been successful at verifying operating system code. So that's a positive aspect. And surely those people making these verification tools are working very hard as well. And those tools are probably better than they were 20 years ago, whatever. But for the Linux kernel, we have another problem, which is if you work really hard and verify those 27 million lines of code today, unfortunately, tomorrow, next week, next month, or something like that, all of your effort will be wasted because thousands of new patches will have been accepted and the code will be completely different. Sometimes these patches optimize things, fix bugs, and sometimes they, of course, introduce new bugs, and so that makes the verification process more compelling, but it still makes it harder as well. So our basic idea is that basically the tool we use for MSC, it's something you have to specify preconditions, postconditions, and loop invariants. Maybe there'll be some changes that are just going to be somehow orthogonal to that. The input and out behavior are going to stay the same. And so maybe over some of these changes, we can actually keep our specifications. That would be nice. The nice aspect of SMT solvers is you give it point A and point B, and it figures out how to get from one to the X next. So if there's something that has changed in between, if it doesn't have any impact on the input-output behavior, maybe everything will go through. Who knows? So in our particular work, we're interested in proving the correctness of Linux kernel code. The code should be as it is. And we're focusing on core functionalities. Probably 27 million lines of code is not very realistic. We want to see to what extent can we port these specifications from one version to the next. And ideally, someday we would like to achieve uptake from Linux kernel developers, just as we managed to somehow achieve uptake from Linux kernel developers with Coccinelle. Maybe that's too much to ask, but we can try. So we're trying with this function. This is our first example we looked at. Should we balance? We actually saw this in the load balancing that I talked about a few minutes ago. The question is, should a CPU try to steal a task during load balancing? Basically, we may have many CPUs that want to steal at the same time. We don't want to let them all steal, because then the task will bounce around between them. So this is a function that has existed since 2013. So it was about 10 years old when we started working on this. It's something that's refactored from other functions. The initial version was buggy, so that's already not great. But actually, the bug was fixed by the humans before it was actually released, so that's not too bad. And it has existed in 10 different variants, so it's not something that changes every week, but it has changed over time. Keisuke is my PhD student who worked on this project in the beginning, and just in doing the verification for this function, he found another bug in the function, and he proposed it to Linux kernel developers. It was accepted immediately. So basically, the idea that we have a CPU, the input is the CPU that is trying to steal, and some information about the context, and it is going to elect an idle CPU that should be allowed to steal, and if there is none, then it elects some default answer, and then it sees if it itself is the same as the elected one. So here's the code. It's not really necessary in the context of this talk to understand it all. And here are the pre and post conditions. Basically, you can see that it's a little bit complex because we have 3 different situations. If it's newly idle, then we want to allow it to do load balancing. And then the other 2 cases, if we find something a core that is idle, a CPU that is idle, the first one should get elected. And if we don't find one, that's the second behavior here, then we should pick a default one as the elected one. So you can see the specifications are a bit voluminous, and probably in the few seconds that you have to look at these, you probably do not fully understand what is being expressed. In our experience, this is kind of a problem. Often we ourselves, from one day to the next, also do not understand what's trying to be expressed. And trying to prove incorrect things is kind of the hardest part of this whole process, because you will not be able to prove incorrect things, but you don't actually get any feedback about what's gone wrong. We also need to have loop invariants. And here the things are fairly simple. In this particular case, basically the idea is we go around this loop until we find the idle CPU. And so the main part of the loop invariant is this one here in the middle. And basically what it's saying is that all of the CPUs that we have checked so far are not idle, because we're just moving along until we find the idle one. The rest of it is just kind of noise, just to show that our loop is going to terminate. And so on our test machine, we have this code, we have the specifications, and the proof takes around 1 minute, which is perhaps completely acceptable. And so here we have the history of what this function what has happened to this function over time. So we have about 10 changes plus that one we added ourselves. Some of these changes have been very simple. One of them just changes comments, so that certainly leaves the specification as it is. Another one, however, does some refactoring, so you see actually a lot of lines change, but the actual behavior of the function stays the same. And so then in that case, the specifications manage to stay the same as well. So that seems like a successful experiment. Some of these other changes are changing the behavior, but in some very simple way. So for example, they realized that actually people can remove CPUs dynamically in the Linux kernel. And so if a CPU has been removed during the time between we called this function and we're doing the analysis, then that's not really an ideal candidate for load balancing. So those add some extra conditions to the beginning of our specifications, but maybe these are things that we could expect a Linux kernel developer with some experience could do by themselves. On the other hand, we're going to see that some of these changes are a bit more invasive. One of them here is, basically here we're changing the algorithm, And when we change the algorithm, what we do, there's the idea of a hyperthread. So actually you have a physical CPU and it's trying to run 2 or 4 application threads at the same time. So that can improve your performance, but it's not as good as putting those things on a core where all of these CPUs are completely idle. So it wants to make 2 choices. The first, it's like the highest priority is one that's fully idle, but it wants to remember along the way if it sees anyone that's partially idle, because that would be a good fallback instead of taking the default one. So this adds a few lines of code here in the middle. On the other hand, it has a really big impact on the specifications. So I explained previously that the loop invariant was this simple thing where we're just moving along and everything before was idle. Now we have basically a little state machine that remembers if we have seen a fallback one, then we have to remember it and we have to remember about its properties, as well as moving along and seeing that we have not seen our ideal case yet. So this gets a lot more voluminous, a lot harder to understand, a lot harder to get things to work out. I don't remember how long it took to do this. I would say maybe a few weeks to get everything to fit together in the right way. And then we came to this one. In this case, we realized that we have this idea of hyperthreads, and we have this inner loop where we want to check to see if all the hyperthreads are idle. And being a hyperthread hyperthreads are in an equivalence class. So if 0 and 4 are hyperthreads of each other, when you're checking 0, you'll check 4, and when you check 4, you check 0. So that is repeated work. So the idea here is to add this CPU ask and not function, and this will remove things from the set of CPUs that you're considering, and then that will be more efficient. And this took us actually months of effort to prove. We're making side effects and we have aliases and it's inside a loop, and it was a complete nightmare. On the other hand, we found a bug, and actually that's the experience we had. At some points we change the algorithm and things get much more expensive or much more costly from a proof point of view, but we actually found bugs whenever that happened as well. Skip this. So basically, our observation is complexities in code are magnified by complexities in the specification, magnified by the proof effort, but changes in the algorithm result in bugs in the code. We would like to develop some tools that can help us. Maybe one of the biggest things is managing aliases. We're not very interested in strange overlappings of data structures, but FRAMAC is considering C. Everything's a pointer to some space in memory, and so it tries to be safe, and this causes a great deal of problems. If you want to look at our code, it is here. So in conclusion, many tools have been developed to find generic bugs and to perform cleanups. At this point in large software, find bugs, Coverity, C-lang tidy, semgrep, and so on. Coccinelle complements those tools by allowing the developers, Coccinelle is not a black box, it's something that's programmable by the developers. But there's still a gap. The real hard problems in getting our operating systems to actually do what we expect is also, we need to also be considering more the algorithms, specific algorithms. Is the code doing what we expect? What do we expect the code to do? What's going on at this level? So we think maybe verification can help. It's an experiment, and we'll see in the coming time. So thank you very much.
If you have questions, please come to the stand, mic stands. There are 2. So you may want to introduce yourself and then ask questions.
Hello? Oh,
yes,
perfect.
Thanks.
Hi, my name is Song from NYU. I also was at your talk yesterday, and I think it was really wonderful hearing about how you found like an actual bug in work conservation, or I guess mispreservation of work conservation in the Linux scheduler. And I think it's, we have a lot of ways to, obviously it's not enough, but we have some ways to find certain bugs in the Linux scheduler or more complex programs. But I'm also wondering, what are some ways to produce concrete and convincing kind of examples to show that this bug is indeed worth investing effort into fixing, and showing that maybe producing interesting cases where, producing interesting workloads where this work conservation bug indeed does lead to severe performance penalties or something like that?
Yeah, so I think that's an excellent question.
No.
I have no answer. Yeah, I mean, it's a hard problem because a lot of these bugs are problems that accumulate over time. And so it's not like a null pointer dereference or something like that. You just create a null pointer dereference in your random piece of software and it'll crash and everybody will be convinced that that's a bad thing. But these are more, the Linux kernel doesn't know what your applications are going to do in the future, so it can only rely on the things that have happened in the past. And so it's hard, yeah, I don't really have a good answer for that. There's a lot of interest in, there's a lot of interest in the Linux kernel community in some kind of verification, some kind of specifications, but also in how can we make better test cases. We have the infrastructure for running the test cases. We just need to know what the test cases should be.
Thank you.
So, thank you.
Hi, Jeremy, Rochester Institute of Technology. Thank you very much. I'm curious, in your discussion of Coccinelle and porting it to other languages, I'm curious if there are any insights about the, generalizing the infrastructure to other languages that have come up as you're doing that porting. Because before starting a PhD, I was a software developer, was doing a much less programmatic, or much less rigorous kind of similar work, and I'm curious about how you translate it.
Okay, so that's a good question. So for Coccinelle for C, that was we started the development in 2004. There was not really a lot of infrastructure or good infrastructure for making this kind of thing, and so we implemented everything by ourselves. So we have our own parser, which keeps track of, I mean, if you make your own parser, it does what you want. So it keeps track of white space and comments, which is not really traditional for a compiler. We have our own AST, you know, everything is designed in the perfect way for Coccinelle. More recently, a couple years ago, we wanted to explore Rust. No one who in my team actually knew Rust at all. And so we didn't really want to plunge into making a Rust parser and so on. We didn't want to go take that route. So after some discussion with people, we took Rust Analyzer, which is basically a parser and has some analysis infrastructure for Rust. And so Coccinelle for Rust is completely built on that. So we have some insights about that. Basically, I mean, Rust Analyzer is interested in keeping your comments and white space and stuff like that, so that was all good for us. On the other hand, when you take somebody else's parser, then things are organized according to their vision of things. And in Coccinelle, we have our meta variables like expression and type and stuff like that. We have designed them and they're supposed to communicate to the Linux kernel developer. Early experiment somebody wanted to change all of the certain type to be something else. They had a type meta variable, and that was only matching certain kinds of things because we were very tied to the Rust AST, which only has types at certain levels, even though humans think of certain other things as types. I don't remember the details anymore. So when you take an existing infrastructure, it might not exactly correspond to your exact requirements. But we definitely got things off the ground. So that was good. Another issue that we had is pretty printing, formatting, and so on. And yeah, I mean, I guess you can imagine the issues you have in that respect as well. So it's not 100% win as we had hoped for. So,
okay, thank you.
Hello, Jean Pichon, Aarhus University. So with respect to the sort of verification side of the talk, I have some colleagues who were looking at completely different parts of the Linux kernel, trying to write specifications, and hoping to find bugs by sort of confronting the specification with the code. And their experience was that basically they found bugs by writing the specification, and not so much, once you have the specification, confronting it with the code. Can you say whether that matches your experience or whether you have a sort of different?
Yes, so in the talk I mentioned one bug that was found by Kisuke, and he found the bug by making a little graph describing the different cases for the function. So that was totally before he sat down to write the specification. So that matches your experience. I think in some other cases, maybe the bug becomes apparent in the proving process, not because the SMT solver says there's a bug here on line 27, but because the SMT solver refuses to prove the thing that you expected was the specification, and then eventually you realize that, oh, it's a bug in the code. But unfortunately, verification only tells you that your specification matches your code. It doesn't tell you when and why things don't match. So I mean, I more or less, yes, agree with the experience of your colleagues, but I hope that if they found bugs that it was useful.
Okay, thank you.
You're welcome.
Hi, Gavin Gray, Brown University. So with the specifications, are they checked into the upstream Linux kernel code base, or are those managed by you in a fork somewhere?
So at the moment we're just doing very preliminary experiments, so nothing is up in the Linux kernel code base. There is a separate effort, though, by Linux kernel developers where they want to put human-readable specifications. So there is one commit, I don't know what's the status of it at the moment, that has a big comment before the function, and there's a bunch of ifs and stuff like that. A bunch of bullets and a bunch of ifs, and they supposedly this natural language is supposed to be machine readable, but we haven't looked into that, and we haven't looked into whether we can actually take those specifications and prove something.
And what would be the goal for managing the specifications in the code, right? If this afternoon I have a really brilliant idea to update that scheduling code and then I break your specification, is there any goal to automatically detect that break, or is it just your PhD student watching the changes to the code?
Yeah, again, I don't have an answer to that at this time. I think part of the important direction is how can we manage that? Even just like, should the specifications be right in front of the function? They get pretty big. Should they be off on the side? If they're on the side, no one will see them. It's all it remains an open question.
All right, thanks.
Hi, Steve Blackburn,
Hi.
Google DeepMind, Australian National University. I really enjoyed that talk. I really like the interposition of rigor and the Wild West of the Linux kernel. One thing that was kind of nagging in the back of my head during the talk, and then something caught my eye on when you started talking about should we balance, and there were 5 words there. It said extracted from scattered existing code. Like this policy that you were looking at had been kind of teased out from scattered bits of code. And I'm not sure what my real question is, but there's something there that I just wondered about how you thought about the idea that key semantics, key policies may just exhibit in the Linux kernel through scattered code, and whether you'd looked at that at all, this question of gathering stuff from scattered code, or if that's something you'd considered at all or about to consider, or had any thoughts on.
I mean, it's not a specific problem that I've looked into. The thing that we do observe, though, is that when they gathered it from the scattered code, they had a if condition at the end, which was completely backwards. It's like a equals or not equals interchange, and surely that was something that was meaningful. Maybe that was the right way for it in the original code, and so that's definitely seems to be a source of problems, which is when you pick things up in random places and put them together, they might not mean what you expected anymore. Thank you.
Okay, thank you. Let's take the last question over there.
Hila Pelg from Technion. Thank you so much for a wonderful talk.
Thank you.
Now, Coccinelle has been in the hands of users for quite a while now, and I'm curious as to what kind of suggestions or requests you've been getting from your users, and if any of them have been interesting enough to act on.
I mean, we get lots of questions. I mean, there's definitely different communities of people. There's the ones who know what Coccinelle does and know, you know, they don't really have time perhaps to do it themselves. That's kind of what I illustrated there. There are other people who do simple things by themselves. There are other people who do very complex things by themselves. Like, I mean, obviously the only interaction we have with people is, you know, they ask questions on the mailing list, and so I can see, you know, are they asking a very basic question as their first question? Are they asking a very complex question as their first question? I'm not sure if there's any questions that have prompted us to do something. I would not say no. Maybe somebody has asked a question that has prompted us to make some change. I think we have gotten some questions that like new, you know, to make it smarter in some way or something like that, and we tend to resist those questions because the tool does what it does, and if you are not happy with what it does, then you have other options. We're not trying to make a tool that will do everything for you. We're trying to make a tool that will do some predictable thing for you. It will do what it does in sort of reliable way. So,
Thank you.
You're welcome.
Okay, really last question.
Okay, hi, Gergely. So in the very beginning, you had this example of the k-malloc versus kzalloc, and the one that you showed first, the first version, the simpler version, of course, had a bug in it because the size that you're allocating and the size that you're zeroing out, like if you go to the version of this with this semantic rewrite thing, this one, right? So of course the value of E1 can change in between because this is C. And it could be, so my question is whether you thought about like not syntactic but like semantic restrictions. Like if I do something like this, I really want to say that the value of E1 doesn't change between, you know, the k-malloc and the memset line. And of course this depends on the semantics of C, and then it's not like you have to understand what the ... does. But is that something that could be...
Okay, so yes, so there's two parts to this question. One part is E1 itself. Why didn't I put some constraints on E1 here? So this is a place where we are relying on the knowledge of the Linux kernel developer. E1 is never going to change. E1 is always size of...
I mean, that's what you hope for, but you know, like...
No, that's what the Linux kernel developer has in mind. We you know, Linux kernel developers have their habits, and the code is reviewed by people who have the same habits, and there's like a collection of habits that are acquired over time. I mean, but there would be no problem. I mean, if you wanted to make it somehow more defensive with respect to E1, that would be fine. I'm just saying that in the last 20 years, I have never actually been motivated to do that.
I guess my question is,
okay, so sorry, let me answer the second part of the question, which is, which I understood implicitly to be, you know, why do we have to write these things by ourselves? Why don't we let the tool do that? And so very much one of our original goals was that we want the developer to understand what's going on. And so we made a very explicit decision not to do any kind of program analyses, alias analysis, anything like that. We don't want to do that because it's hard, that becomes harder for the programmer, for the Linux developer to anticipate what are the approximations that might be happening and what kind of answers we will get out the other side. So we give the developer a sort of rudimentary language for expressing these kinds of things, and we rely on them to know what kinds of things typically change in different parts of the code.
Okay, I see. So the transparency of the process is an important
Exactly.
part. Okay, yeah. Thanks, gotcha.
Okay, thanks a lot for the great question and answer. Let's thank Julia again.